Hey, year 12s, thanks for coming along, guys. I'm just going to wait 5 seconds because I need to pause the video that's on my other screen, because otherwise you just hear me on YouTube. Come back. I'm really hoping I've got the right one. There we are. And my other screen. Pause. There we go. Winner, and then I can move the chat up. Cool. We're in. So, guys, this is the last lesson of equilibrium. I'll cover all the various bits that I need to, and then so I'll do share screen, that one, get rid of all of this jazz. Getting there slowly. There we go. Hide that bit, and we're in. Okay, guys, so last lesson of equilibrium today for AS. So we're looking at industrial equilibriums today, and particular equilibriums of focus for EdXL. I like it. Got Sian saying hello. Got Epicos, which I'm assuming is Oliver, and then Niazi, I think is Shazza, and then Didney, don't know who that is. Ava. It's hard for me to comment on students when when their names don't match. Whatever. Okay, so what I want to do is I want to go through just the industrial equilibriums and the equilibrium graphs that you're going to then come across. So the first thing I want to do is I want to tackle 2 equilibriums that you guys need to specifically know about for EdXL. So the first one is iodine and chlorine. So, okay, so this is equilibriums to know. Yeah, and in reality, that this is kind of, this includes the industrial ones as well. So, but as I said, certain equilibriums are done by EdXL more than others. So the first one is the reaction. So is the reaction between iodine. And I want to actually do the 2 stages in the reaction here. So the 2 steps in the reaction is iodine, which is a gray solid. Yeah, gray solid reacts with chlorine gas. And what that will become is that will become iodine trichloride. Now now notice it is not an equilibrium. Yeah, it is not an equilibrium. Now, just to give you the state symbols, chlorine is a gas at room temperature, and iodine trichloride is a liquid. And just to tell you a little bit about it, it's brown. It's rather a gross-looking liquid. So we've got grayish-black iodine. This is where I quite like adding colors and information because you need to know the group 7. So you've got grayish-black iodine, yeah, just gray solid. You've got green chlorine gas. See what I did there? It's like a cloud. Oh, moving on. And then you have a liquid, which is like a dark brown liquid. It's like a browny red. It's like a rusty kind of color, orangey brown. It's not dark enough. This is where I quite like to have more colors. Brown. Yeah, it's kind of what the color is there. And I'll go for that one. So you end up with iodine. There we go. So you end up with iodine trichloride, which is a brown liquid. And that's not an equilibrium. So now, what now happens is that iodine trichloride goes through another reaction. And this one is equilibrium. So you have iodine trichloride reacting. Oh, by the way, I need to balance the equation. Hate not balancing equations. And 1.5. I love halves now at A level. So you take iodine trichloride, you react it with another molecule, another mole of chlorine, and we establish this equilibrium of iodine tetrachloride. There we go. ICl5. Now what that looks like is you end up with your brown liquid reacts with your green gas, and you actually form, I believe, iodine tetrachloride is a yellow solid, I believe. It's nice for me to check that. Let's have a look. Iodine tetrachloride, ICl5. Come on, ICl5. Let's have a look what it looks like. Come on, little dappy. Come on. Doesn't work as fast as I do. ICl5. Yellow solid. Come on. Images. Yellow solid. Give me a yellow solid. Yellow solid. Come on. Come on. Oh, it's really slow today. It's sluggish. Sluggish it is. Come on, give me the color. Color. Sorry, it's not there. That's really annoying. Let's go color. Oh man, laptop's really struggling this morning. Really struggling.
Is it because I'm on the internet?
No, probably not. That's irritating. I'm pretty sure it's yellow solid. Gonna give up in a minute. Oh, colorless liquid. Iodine. Oh, that's pentafluoride. Ooh, why is it giving me something which I'm clearly not asking about? Stupid internet. I'm pretty sure it's a yellow solid. Pretty sure. Not that it makes any difference, but it is a solid. That's certain. So it goes from a liquid, a gas, and then a solid. So the reason why this equilibrium is liked so much is because you can do some rather nice things with this particular equilibrium, because you can see a state change and a color change. I'm pretty sure that's a yellow solid. Pretty sure that's a yellow solid. Somebody can check that for me in their own time. That'd be nice. So you can do this practically. You can actually visibly see this. So what you can do is you can set up a rather nice system like this with a U-bend like this. And then you have a cap on the top of it. You have to do this in a fume cupboard because of chlorine. Chlorine is not nice. And then you've got a pipe going out. And then like this. And then you put another cork on the top there. So what you can do is you can react iodine and chlorine together in one vessel. I'll take a conical flask maybe. Not that it really matters. So you can take our solid iodine, you can take our lovely green chlorine gas, you can warm them up together, add a little bit of heat. Don't even need that much heat, to be fair, just needs warming. And what you will make is you will form, and of course the iodine trichloride, which of course vaporizes at this temperature, travels through the tube and it will build up. You put this in an ice bath. Put this in an ice bath. Ice, baby. Sorry, my bad. Put it in an ice bath. You put it in an ice bath, and what you will see form is a brown liquid at the bottom of the tube. And that's the iodine trichloride. It's very, very clear to see. Come on, Lappy. Come on. Really struggling. It just hasn't got enough memory to be able to cope with all of this stuff. Do you want to save snip? No. Is there anything I can turn off my camera because my laptop, it's one of the odd idiosyncrasies about this. I could turn off the laptop. It's an awful lot of effort. Okay, not going to bother. Sorry about this, guys. It's taking a bit more. So we're going to form a brown liquid at the bottom, and that's your iodine trichloride. What you can then do is once that reaction's finished, once you've collected your iodine trichloride, what you can now do is you can add more chlorine. So if we add, so what you'd then do is you'd then disconnect the main reactor. You'd disconnect this guy, you'd seal that off, pinch that, yeah? And then what you would do is you would add in chlorine gas separately through this tube here. I'm just gonna see if I can edit it just a little bit. Now, previously this would have been sealed. I know this looks all a bit crazy. Yeah, there'll be a valve here. Yeah, but anyway. So what we can now do is we can add in chlorine separately from the iodine. So you can add in more Cl. Now, what happens is, it's rather a lovely reaction actually, because it's sealed on both ends. What that means is when the chlorine gas goes into here, what's happening is you're increasing the concentration of the chlorine. Yeah, you're increasing the concentration of the green gas. And what will happen is the brown liquid will solidify and become yellow. Last time we didn't go through cost on concentration. Yeah, that's because I'm roping it in now. Sorry, Oliver. Download some more RAM. Download, Jim Joe. Like, do you have any idea what RAM is? Like, do you have any idea? Download, buy some. You can't really do it with tablets. It's not really that as easy, but that's brilliant. So anyway, so this is concentration. So what happens here is it's a lovely reaction because it's all sealed. So you'd expect the whole thing to kind of explode because the pressure would build up as the chlorine goes in, but it doesn't. What you're doing is you're increasing the concentration of chlorine gas. You're also increasing the pressure. There's two folds of this particular step. So if you increase, question, you can write this down. By the way, I hope you've drawn that diagram because it's a boss diagram. Love that. My diagram's awesome. So question, explain why the yellow solid of ICl5 appears when Cl2 is added in stage 2, which was the pinch the main reaction vessel and then to add in more chlorine. Yeah. So answer, and this is coughs again. We're just straight. This, as soon as you're dropping into equilibrium, you're running coughs on this. So the knowledge here is that chlorine is a reactant. Yeah, this is purely because of concentration. When you add more chlorine, when chlorine is added, we're increasing the concentration of chlorine. So the knowledge, I'm just going to put that as answer like that. Knowledge is that Cl2 is a reactant. That's the knowledge. It's on the left-hand side of the equation. Yeah. So oppose. If we increase Cl2 concentration, then the equilibrium. I'm being like I am in an exam here. Sorry about that's meant to be an I. Equilibrium will reduce concentration, reduce conc of chlorine gas. Right, how's it going to do that? By favoring what? Right, this is the scenario. So hang on a minute. What's it going to favor? It's going to favor, this is the only time you're allowed to say this. It's going to favor the forward reaction. Yeah, that concentration is the only time you ever mention forward or backward. It's going to favor forward reaction because the favor forward reaction because that reaction is the one that destroys the chlorine gas. It's one that removes it. Yeah, favor forward reaction, shift from left to right, increase yield of ICl5. There we go. Love it. Now it's a lovely reaction because you see the black solid. You know what I'm going to say? I've got an idea. Okay, considering my laptop is struggling enough already, let's just max it out. Why not YouTube? So I'm going to add this to the notes. You guys can have a watch of this video because actually it's quite a cool thing to see. Usually we'd set this up in school and you'd get to watch it, but obviously I'm now can't. God, you're doing chemistry. I miss my chemistry. Oh. I miss trying to set fire to Oliver. I mean Ava. No, I meant the tables. Tables. Yeah. Yeah, that's what I meant. Let's do ICl3. Oh, you see, the problem is my laptop is now seriously ICl5. Go. Look, it's not even typed it yet. And then mental. Come on, little lappy. Come on. Come on, boy. Come on. It's just not having any of it. I've just maxed this thing out, man. Really, really struggling. The funny thing was, it didn't struggle so much. How's my battery doing? Is this turned right? Yeah, maximum performance. Yeah, best performance. All right. Are you watching a video, are you? Oh, it's possibly why.
I'll just stop it. So
No, it's fine. It's fine. No, that's part and parcel of the gig, babe. You've got to do your work too. Right. Where is the reaction? The problem is, it probably wants me to write in the words. Has it even searched for it? It hasn't even searched for it. Guys, do me a favor. Do a search for iodine trichloride with iodine pentachloride. That would be really handy. And then watch the video. Yeah, I'm just going to close that down. There's no point. Laptop is literally maxed out here. Okay, so yeah, I need you guys to do me a favor. Can you go and watch YouTube for this, please? That would be fab. YouTube. Go and watch the YouTube video of that one. Right, next one. So now that we've covered that guy, we could also, by the way, recognize that we're also going to increase the pressure. Oh, just to say, there is a second part to this experiment, which is if I then, once this is all done, if I reseal it there, and I remove the cork, what will happen is that the yellow solid will turn back into the brown liquid. It's kind of nice, actually. So this is kind of a second part of this. And the reason why, I'm not going to spend ages doing this. There's no point. You remove the cork and it lets out the pressure. So the pressure drops. Now, if the pressure drops, the equilibrium, is going to try and compensate for that pressure by making more gas, which means you're going to be moving in that direction to make more chlorine gas, and it turns back into the brown liquid. It's rather a lovely practice, rather a lovely demo. Unfortunately, not a class practical because it's a nightmare to set up, but great demo. Okay, next one, folks. Next one is NO2 and NO2. In fact, I may as well just write the equation. EG number 2. Example number 2. So this is NO2 forming in equilibrium to form N2O4. And there's 2 of them. And this is a gas, and this is a gas. Now, the reason why this one's a really lovely one to see is because NO2 is a brown gas. NO2 is a horrible, toxic brown gas. Very acidic, also causes edemas in your lungs. Not very nice gas, that, pretty toxic. Now, N2O4 is a colorless gas. That one is colorless. So we've got a brown gas, and a colorless gas. Now, this one, do you know that this is one of Le Chatelier's original experiments? It's really cool, this. This is like over 200 years old. It's amazing. And he discovered this reaction. It was one of the main pieces of evidence that he had of chemical reactions being in equilibriums. So what he discovered, so here's how you do this experiment. So what you do is you take a conical flask. My diagrams are amazing. You add a small amount of concentrated conch nitric acid. That's terrifying, by the way. And you then add some copper. Yeah, you add some copper metal. Cu solid. So concentrated nitric acid, just so you know, is a liquid technically rather than aqueous. It's conch, which means there's no water. So it's not aqueous. Now, what that's going to generate, this reaction, I'm gonna give me a side tube. I think a side tube is just easier rather than, I can do a delivery. No, I'm just gonna do a side tube. There you go, side tube, cork. Right, so what this is gonna generate, toxic brown NO2. That's what it's gonna generate. It's gonna generate toxic brown NO2. Now that NO2, of course, is gonna come through the delivery tube, and what we're going to collect it in is a gas syringe. We're going to collect this in a gas syringe. Sorry for my poor gas syringe. You have to, whenever you draw a gas syringe, you must include the scale, by the way. So this brown gas is going to fill the gas syringe. Like that. There we go. Now, once we've got, by the way, I'm pretty sure anyone who had Cyan, Marcellus, and Russell, you guys had me last year, so you probably actually saw me do this practical before, and generating NO2 and reacting conch nitric with copper. It's an amazing reaction. So what you end up with now is this brown syringe of NO2. Now, what you can now do, now that you've got this brown syringe full of NO2, what you can do is you can unclip it and seal it. Just cap the gas syringe. Now, this is a brown gas. Yeah, I'm actually going to give you a much more realistic color. I say brown, and it is brown. It is. But the brown color is quite obvious. The brown color is a bit like this kind of color. It's a bit that's not the color I chose. There you go. So the brown color There we go. I'm going to try and make that a bit thicker. The brown color looks like a bit like this. Now, there's a really cool thing that you can do with this because it's a gas syringe. I apologize for the length of the syringe being bad, by the way. I'm going to have to push it more than that. So there we go. There's my gas syringe. What we can do is we can compress the gas. We can squash it. So if I push the plunger, plunger, can't spell plunger, sorry. Push plunger down. What's going to happen is I'm going to compress and raise the pressure of the NO2. So the cool thing is there's going to be two observations now, which is really neat. So would anyone like to offer me on the chat what the first observation is going to happen? If you take a brown gas and you were to squash it into a smaller area, what's going to happen to the color of the gas in the plunger? You guys can just have a think about that. I know that there's a delay. So, by the way, I'm going to need to draw two of these. So while you guys are having a think, while you guys are having a think about this, I'm just going to clone that. I know it's a terrible plunger. I should have actually, what I probably could have done is to actually, if I do home, copy, that's clipboard, copy, there we go. And then do paste, there we go. Sorry, but I could have actually found pictures of syringes. It's going to get darker. Well done, Jim Joe, spot on. Becomes lighter and eventually half colorless. No, definitely not. Jim Joe's spot on. Jim Joe, really impressed. It's actually initially, this is where, so initially you're going to see two observations. Initially, you're going to see it get darker. The reason why it gets darker is because, this is where I need to go really dark here. It's going to get darker because you've compressed it into a smaller area. Yeah, so you've taken a lightish brown gas and it gets much darker. And this is the initial observation. And they love this at Edexcel. This is initial observation. Now, Le Chatelier did this, by the way. He actually witnessed this and wrote down in his diary in rather poetic French about this. He also has a really funny story about his use of nitric acid and copper to make the gas and how he spilt it on his pants and it dissolved them. It's quite entertaining. You should try and look it up. There's quite a funny story about it. But then, moments later, yeah, initial observation is darker. This is because you've got the same amount of dark brown gas in a smaller area. Concentration increases. Pressures increase. Concentrations increase. It gets darker. Moments later, yeah, a few seconds later, you get a second observation, and that it becomes paler. Now, the really weird thing was, for Le Chatelier, it became paler than the original mixture. And that was super weird. It went from being, the expectation of it getting darker was kind of like, yeah, totally expected that. Yeah, it's going to be in a smaller volume, so it's going to get, but then it went lighter than the original. Now, what a really bizarre observation. Yeah, it tells him that there's a chemical reaction going on inside the vessel. So we can look at this from a pressure standpoint. So we have brown NO2 going to form colorless N2O4. If you're interested in what these gases actually look like, it's the best way of me to do that. Is that a good idea? Probably not. Probably not a good idea, to be fair. There we go, NO2, two of those, going to form N2O4. Eek, that's not going to be a nice picture, actually, is it? It's not going to like this at all. I'm not entirely sure, actually, if that's actually entirely correct. I think that's possibly what happens. It could just be the fact that it has a double bond. I don't think that's the case, though. Sure, it's going to be in a resonance. Anyway, not that it really matters. So they join together, and I shouldn't really do that. Don't even need it for the lesson. Don't even need it. I'm going to have to look that up now. It's going to bug me. So anyway, so we increase the, let's run cough. So what we've done is when we push the plunger, we question, decrease volume. Decrease volume. which we know is otherwise known as an increase in pressure. Yeah? And they're going to say explain. And you're running coughs. Yeah? Knowledge. We know that pressure is all about coughsy. So we can go knowledge. There's 2 moles. Pressure is all about moles of gas. We've got 2 moles of brown gas on the right, and we've got 1 mole of colorless gas on the left. So 2 moles on left, whereas 1 mole on right. On right. If we increase the pressure, then the equilibrium will reduce pressure by favor side with less gas. Shift will be to the side with less gas, so shift left to right. Yield of NO2 colorless gas will increase. Yield of colorless N2O4 increases. So it gets paler. It's a nice question. Edexcel love this one, so I have to do this in the lesson. Got to cover these 2 experiments that they love to ask about. But if the volume is getting smaller, won't it get more concentrated? Yes, Jim Joe, concentration is the same as pressure in gases. They are literally synonymous with each other. You don't tend to talk about concentration in gases context, but I mean, we did in the case of the chlorine one. It was kind of the same thing. I know you're going to say increase the amount of chlorine. Yeah, its concentration increases, therefore the pressure also increases. You could say the pressure of chlorine, they'd allow that, even though you probably wouldn't want to. But I hope that makes sense. I know that's tricky. I haven't really made that very clear, have I? It's really funny. With gases, you talk about pressure. Yeah, and they'll always allow it as long as you've done that. Okay, right, guys. So now that we've covered the 2 experiments, which are so decrease in volume equals increase in concentration and pressure. Yes, in a gases situation, yes, of course it will. If you've got a closed system, remember that term? We had that in our nota bene, closed system. We had this in one of our lessons. Yeah. I'm going to ask anybody on the chat, please. What's the definition of a closed system? Who can remember? Yeah, so in a closed system, if you take a gas and you squeeze it and you reduce its volume, you must increase the pressure. Those 2 go hand in hand. And pressure is the same thing as concentration, but in gases. So the Koch's process is almost the same. It's not the same. You talk about pressure and moles on each side. A system where particles cannot enter or exit. Thank you very much, Jim Joe. Spot on. Reactants and products can neither enter nor exit. Well done. Great job. Good man. Well done. Great job. Jim Joe, it's so nice to see that you're reading the notes that we made in previous lessons. I'm really impressed, dude. Keep that up. Yeah, I hope everyone in the class would be doing this. Okay. So, guys, we now need to do your industries. New title, please, in the subtitle. Industrial equilibrium. Industrial equilibrium. Equilibrium. Industrial equilibrium. That was tricky, that I had way too many syllables. Right, industrial equilibriums. Which ones do you need to know? Number 1, Haber. Good old Haber. You need it from GCSE. You know this. To make ammonia. To make ammonia. I like it. Number 2. You need to know the contact process. Contact. Haber process. Process. Oh, no, gone Yorkshire. Contact process. Make sulfuric acid. H2SO4. Sulfuric acid. Hello. Number 3, direct hydration. Direct hydration process. Hydration. Direct hydration of ethene. That's to make ethanol. Makes ethanol. It's our Friday night molecule. Gotta love a bit of ethanol. Cool. Is there any other industrial equilibriums that I think you need to know Nah, not really. Can't think of any more off the top of my head. I'm sure there will be loads more of them. But these are the three that come up on a regular basis, and you need to know your conditions. Okay, so let's look at the equations. So I'm going to do the equations in blue. Why not? So this is N2. I'm going to make my pen a bit thicker, I think, at this point. It's just I'm getting further away. N2 plus H2 form ammonia. Let's balance it. Balance the equation. The equation. It's French for equation, by the way. Let's do that one. Winner. No, wrong person. Wrong person. There we go. So this process is to make ammonia. We take nitrogen from the atmosphere. The resource, the resource where these things come from. So this is the resource. The resource is the atmosphere, ATM for nitrogen. This one is the electrolysis of brine. Yeah, and ammonia is used to make fertilizer or explosives. Fertilizer. There we go. Used to make fertilizer. Can I emphasize the make? Yeah, you can't say used as fertilizer. No, ammonia is a weak base with pH 11. You pour it onto your field, you're going to kill everything in the zoo. And plus, it's dissolved in water, so if you pour it on it, it'll just evaporate out the gas anyway. So just bear that in mind. Used to make fertilizer. Yeah, I'm just checking my phone. It's telling me my lesson's coming to. Oh no, I've still got. I'm all right. Right. So it used to make fertilizer. The conditions, you want to switch to red on this one. You just got to know these guys. The pressure for this, pressure is 200 atmospheres. Holy moles. Guys, that be crazy. Is hydration of ethene also called hydrogenation? Oh my God, no. Is that Shazza? No. Hydrogenation has the word hydrogen in it. So, oh my goodness, hydrogenation is the addition of hydrogen. Yeah, that is not the same thing. So, just to show you, hydration is the addition of water. So here's ethene, here is water. We push those two together in equilibrium, and I'm going to form ethanol. Yeah, I'm just showing. I ought to color code this to show you the atoms that are joining. I'm going to color code that because I am awesome. I'm going to color code it. So I'm going to do the water in blue. See what I did there? Because water's blue. No, all right. I'm gonna shut up. So there's the water molecule that I've done. These are the originals. Come on, red. Come on. Ah, you're so slow. There we go. The direct hydration of ethene to make ethanol. Yeah. Shazza has just mentioned hydrogenation. Hydrogenation is another alkene reaction, but in this regard, I'm adding ation often means reaction really in this case, but hydrogenation is the addition of hydrogen. Just going to show you hydrogen gas in the form of, I don't know, pink. No, it's too close. Purple, orange, yellow, green it is. So hydrogen gas, it didn't do it. That's amazing. Great job to computer. So we've got hydrogen gas, and if I do hydrogenation, oh my goodness, it's so slow. Hydrogenation, and I'm going to form this guy. You get rid of the double bond. Yeah, hydrogenation just gets rid of it. It turns it from an alkene into an alkane. It's used to turn vegetable oil into margarine, if anybody is interested. Yeah, and notice how the hydrogens go across the bond. They go onto separate ones like that. Yeah, one hydrogen goes on each one of them, goes across the double bond. That's hydrogenation, Shazza. Hope that helps. Of brine. What does the underneath electrolysis of brine? Yes, of brine. Yeah. Salt water, brine. Yeah, electrolysis of brine. If you want to put seawater, you can. Seawater. Salt water, sodium chloride solution. They prefer sea watch. What's wrong with me? I don't know what's going on with me there. Hang on. Sea water. There we go. Right, 200 atmospheres, that'd be crazy pressures. Right, why don't we go above 200? Yeah, no higher. No higher. Cost of equipment to do so would be crazy. Cost of cost of equipment, and danger of explosion. Yeah, definitely a bad idea to go any higher than 200. It's expensive enough as it is. Next one, temperature, 450. 450 degrees Celsius. Compromise. Because the forward reaction of this is exothermic. What that means is that kilojoules per mole. So what that means is I should be lowering the temperature for a bigger yield, but compromise, reasonable rate, we did this in our previous lesson, reasonable rate, reasonable yield. Yeah. It's all about the balance between rate and yield. Catalyst, iron. Catalyst is iron solid. Solid iron metal. Love it. Right, next reaction. Contact process. This is where I need to move everybody down. And nuts. My laptop is really struggling with this as well. Oh no, it's not going to work. Oh, it does. Oh, it did. Oh, no. Nope. It's really struggling. There we go. Okay, contact process. For making sulfuric acid, let's do it in blue. So at this point, just to explain, sulfur reacts with oxygen to form SO2, not equilibrium. SO2 reacts with more O2, with another half O2, in equilibrium, oh, made a mess of that, in equilibrium to form SO3. SO3 reacts with sulfuric acid to make oleum in one direction, H2S2O7, called oleum. H2S2O7 reacts with water to make 2 sulfuric acids. 2 sulfuric acids. Now, the only equation that you actually need to know is the equilibrium one. So I can get rid of the rest. But these have appeared in various questions, these. Oh, I'm not going to delete it. I shouldn't delete it. Yeah. The only one you guys need to know for equilibrium is that guy. So we need to know the conditions for that one. Yeah. So what are the conditions for this? I'm going to do this in red. So the conditions are pressure of all gases. The pressure is 2 atmospheres. That's weird. The reason being is that's really strange, that, because there's 1.5 moles on this side and 1 mole on this side. I should be raising the pressure to make more SO3. So why wouldn't I do this? The reason being is the yield is already 95%. There's no point in spending money on expensive equipment when you've already got a huge yield. Already 95% yield. Next, temperature. Temperature is 300 degrees Celsius, I believe. It might be 450. Oh no, I've forgotten. It's 450. It's 450. I'm pretty sure it's 450. I'm going to check. Don't want to write down the wrong number. I've got a number in my head. So contact process. Contact process conditions. I know the lesson's coming to an end, folks. I know. Come on. Come on. Come on. Sorry, folks. 450. I knew it was. Yeah, it's nice, isn't it? It's the same temperature as the Haber. 450 degrees Celsius, exactly the same thing again. The forward reaction is exothermic. So this is another compromise. Yeah, another compromise between rate and yield. Yeah. And the catalyst is V2O5, vanadium pentoxide. V2O5. Cool. Just to show you the catalyst equations, just for fun. V2O5 reacts with SO2 to produce SO3 and V2O4. The V2O4 reacts now with oxygen, half O2, to produce V2O5. It's regenerated, it's not used up in the overall equation. That cancels with that, that cancels with that. The overall equation is the same. Different pathway, but with a lower activation energy. Winner. Nailed it. Next one, direct hydration of ethene. So this equation, do it in blue. We're nearly done now, folks. We're nearly done, nearly finished. Ethene, CH2 plus, that's a gas, plus steam, that's important, not water, steam, yeah, and that's in equilibrium to form ethanol, our Friday night molecule. There we go, which also comes out as a gas, by the way, at this temperature. So the conditions for this particular one, I'm going to move my catalyst equations up out the way. It's nice to be seeing catalyst equations. It's just still it's really struggling. There we go, move that up there. So my conditions, which I will now put in red. There we go. So pressure, 60 atmospheres. Got to know that one. 60 ATM. Now, just to point out, by the way, that's a very odd pressure. Nota bene, yeah. Can't go any higher. Can't go any higher because ethene will polymerize. It'll turn into It'll turn into polyethene and block all the pipes and the whole plant will explode. That did actually happen once upon a time. Did happen. Next one, temperature. Temp is 300 degrees Celsius. 300 Celsius. Again, it's a compromise. It's exothermic in the forward direction. So this is another compromise. They're all compromised temperatures. Compromise between rate and yield. Catalyst. Cat is concentrated phosphoric acid, H3PO4. If you want me to put the name down, phosphoric acid. So you can also, there is an alternative to phosphoric acid. An alternative would be to use concentrated sulfuric acid. Now, we actually use this in lab. If we're going to demonstrate this reaction, we use conc sulfuric because it's actually a better catalyst. But the problem is it also eats all your equipment. So they actually sub out. This is replaced. Sorry, hang on a minute. This is a replacement for conc sulfuric used instead of conc H2SO4 because it's less damaging to equipment. The answer is less corrosive. Less corrosive, so less damage to equipment. Less damage to equipment. Can also say it's actually safer to handle as well. That's also allowed. Safer to handle. That brings us to the end of equilibrium, folks. Those are all the ones you need to know. We're done. Look at that. Absolutely on bob time. That's amazing. Look at that. Oh, no, I haven't done equilibrium graphs. No. Okay. All right. I'm going to do one more lesson. I'm going to do one more lesson, folks. And because equilibrium graphs is only going to take me 10 minutes. I'm going to do one more lesson. Damn. Oh, damn it. Didn't want that, really. Right. There we go, guys. Bring me back. I'm going to do one more lesson on equilibrium graphs. I will rope in a little bit of revision as well. I'm going to post you guys on the Google Classroom. I'm going to post you some equilibrium questions for homework. When's our next lesson? Monday? Don't know. Sometime. Our next lesson is on Tuesday. So on Tuesday, I'm going to go through the questions that I post on the Classroom. I'm going to then cover equilibrium graphs, and then I'm going to set you your test as a homework because I can't lose a lesson. I'm going to see you guys soon. Take care, guys. Have a good day.